Alright class, let's talk about casework today. Now casework is one of the most fundamental counting techniques that you will learn about, so it's very important that we get really good at this. I would say casework is part of what I call the big four in counting. So for those who don't know, the big four includes casework, what we're doing today, something called complementary counting, something else called constructive counting, and then finally the principle of inclusion-exclusion. And all of those we'll learn about in future videos, so don't worry. For now, we are going to talk about casework. So casework is probably one of the first things you should try for every counting problem because it comes up a lot. So I would say 90% of your problems can be solved with one of the big four techniques. So it's very important that we learn this. So let's start. So casework involves breaking up a problem into two or more what we call cases. So what we do is we break up the problem into two or more categories, which we call cases, and then we add up the counts for each case to get the total count. And this will be our final answer. And I'm going to show you how that looks like later down in the document. So you can probably tell, since we're going to be breaking things up, it's very important that we stay organized and make sure that we don't miss any cases. Okay? So the tricky thing is going to be making sure that you did not miss anything. So you want to count everything and make sure you didn't miss anything. When you break up your problem into cases, they must be what we call exclusive. This means every outcome should show up in exactly one case. There should be no overlap between the cases. Again, I'll show you how that looks like in the problems that we do. If you're a little confused right now, don't worry. So we can see casework has a big advantage in that it helps us break things down into manageable, bite-sized pieces. So it takes something that might seem a little difficult at first, but when we break it down, eventually it looks very easy, which we like. We like when things are as simple as possible. Now, as you work through these problems, you'll find that the actual counting is not the difficult part. So when I say actual counting, I mean all the stuff we learned about before. So we have our permutations, our combinations, and our multiplication principle. So that's not really the main concern with casework. A lot of times the hard part is finding out how you actually are going to divide your cases. So that's the big question that I always want you to ask yourself in the back of your head. Always ask yourself, how will I divide my cases? So I've left this huge blank space here because I'm going to add this in later after we go through the problems. When I go back and upload the solution document, this big space will have some tips and pointers on how to split up your cases. Okay? So we'll ignore this for now and let's move on to this thing that I promised you before. So how does a casework solution look like? So when you're working through problems with casework, this is just a little guide that I want you to follow. So if you follow this, you should be good. So as you can see, it's very organized and it has this specific structure. So first we have something called case 1. You're going to write down the conditions for case 1. You're going to use some counting techniques to get a number here, which we've called A. You're going to do the same for case 2, this time with a different condition from case 1. You're going to get a answer of B. Okay, and you're going to repeat this for however many cases you have. So over here, all the way until the end. So I wrote case N, but whether that's 3 cases, 5 cases, 10 cases, doesn't really matter. In the end, your total is just going to be all of these numbers, okay, added up together. And it's very important that you add them up and you do not multiply. With that all out of the way, okay, let's see this casework in action with question number 1. So question number 1 says, this figure shows a road map between 4 villages, A, B, C, and D. The arcs, so this little thing over here, indicate paths between the villages. So this is a path from A to B, and this would be a path from B to D. And the question asks, how many ways can we go from A to D if you can only move left to right? So we want to go in this general direction. So we're not going to go backwards. So for example, we cannot go from A to B and then back to A, back to B, back to A, to C, and then to D. No, that is not allowed. We can go A to B and then from B to D. So let's count. How many total ways are there? So if we are to solve this problem using casework, which is the way to go, how are we going to split up this problem into cases? Now personally, I see a top half and a bottom half in this problem. What does that mean? Well, I see something like this. So we take this problem and divide it into a top half and a bottom half. So the top half would be paths from A to B and then from B to D. The bottom half would include paths from A to C and then from C to D. So then the total count will just be the sum of the number of paths from A to B to D and the number of paths from A to C to D. And then we'll have them all. And we shouldn't miss any of them. So let's start. So, as I said before, the one question we should ask ourselves is, how are we splitting our cases? So to answer that, we are looking at a top half and a bottom half. And that's because a path from A to D requires us to go through either point B or point D. And I'm going to emphasize this or portion because it's very important that it's either one or the other, but it cannot be both. So this is how the solution is going to look like if you follow the guide. So first, you're going to write case 1. Case 1 will be paths from A to B to D. That doesn't really look like a D, so I'm going to fix that. Okay, so let's count this. So first, the number of paths from A to B. You can see we have 2 choices for that. And then for each of these 2 choices, we have 3 choices for the path to take from B to D. This means overall, there are 6 paths from A to D that go through point B. So just to emphasize, this is the number of paths from A to B, and then this is from B to D. So that was case 1. Now case 2 will be the number of paths from A to C, and then from C to D. So let's count this. Similarly, we have 4 paths from A to C, so that's 1, 2, 3, 4. We can take any one of these. We have 4 choices. For each of these 4 choices, we have 5 choices of the path to take from C to D. This means overall, there are 20 possible paths. This means overall, we have 6 plus 20 paths. So that's 26 paths from A to D. Notice that the guide says to add these 2 numbers up, 6 and 20. It is not the same as these 2 numbers where we multiply them, because the reason we multiply here is because these 2 events can happen simultaneously, but in this final count, these 2 cases cannot both be happening at the same time. It is either one or the other. So that's another clue. When you see the word or, a lot of times it means you're going to be adding. When you see the word and, you're going to be multiplying. But again, try not to focus too much on memorizing the words. Just think about it logically, and it should make sense. So that's a point I want to emphasize. The answer is not 6 times 20. Simply because these 2 cases cannot both be happening at the same time. So you can see what I mean by the idea of there being no overlap. And as usual, we have to make sure we got everything. So since we can only either go through B or C, right? There is no E or anything like below here. Well, I think we got them all. Excellent. So that was an example of casework in action. I hope you see it wasn't too terrible. It makes sense too. Here's question number 2. So let's see casework to solve a different type of problem. So before we had a little picture, but this time we only have words. But it's the same thing. So ask yourself, how are you going to split up your cases? It says the people of Math World only have 4 letters. Sounds like a very fun place to live. T, M, H, and A. And every word has no more than 3 letters in it. How many words are possible in Math World? So it says repeat letters are allowed in a word. So for example, we can have a triple A, but 0 letters does not count as a word, obviously, because then that is just nothing. So again, the million-dollar question, how are we going to break up this problem into cases? I'm personally thinking case number 1, what will it be? I'm personally thinking let's break up our cases based on the number of letters in a word. So first, we'll have 1-letter words. So over here we have 4 possibilities, either M, A, T, or H. So the individual letter itself counts as a word. Not bad. Let's make another case, case number 2. This one will be 2-letter words. So, to count the number of 2-letter words, what we can do, going back to our multiplication principle, is we can represent a 2-letter word by these placeholders, and then we'll think about how to fill them in. So, the first letter has 4 possibilities: M, A, T, or H, and then for each of these 4 possibilities, there are 4 possibilities for the second letter. Possibilities, choices, same thing either way. This means there are 16 valid 2-letter words. And yes, there are still 4 choices for each because repeat letters are allowed, as stated in the problem. And then we have our final case. We know this is the final case because in this world, you can't have more than 3 letters in a word. So after we do this, we should be done. So again, a 3-letter word can be represented by this placeholder. Made them really big. So there are 4 choices for the first letter. For each of these, there are 4 choices for the second letter. And for each of these, there are 4 choices for the third letter. This means there are 64 3-letter words in Math World. And again, I want to emphasize the point that there is no overlap between the cases because you cannot be both a 1-letter word, for example, and a 2-letter word at the same time. It's very important that we have no overlap between our cases. This means that overall, therefore, our final answer is 4. According to the guide, 4 plus 16 plus 64, which is 84. That was a horrible box. 84 words in Math World. Excellent. Question number 3. So question number 3 asks us, so we have another picture over here, how many triangles are there? Now you can start counting these however you like, right? You can go like maybe we have one here and another triangle here, but notice we also have this bigger triangle here and maybe this one over here. So there's a lot. So how are we going to count this in an organized and efficient manner? Well, the answer is casework. So let's use casework for this problem, and we're going to divide our cases based on the size of the triangle, because as I showed before, we have many different sizes. So let's do that. So our cases will be split based on the size of the triangle. So in case number 1, maybe we could have something like this. Let's count the little ones first. So how many of these do you see? Count them off. These are all the same size, by the way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 of these. By the way, I hope you can see why I split the cases up like this. It makes sense. So going back to what I said before, a lot of times casework is basically just common sense and just splitting the problem up in a logical manner. Alright, now we got triangles that look like this. How many of these are there? Well, we can count, so we got, that was horrible, don't know what happened. So there's one here, there's another here, another here, so that's 3 so far. 4, 5, and 6. Now, are we missing any more? This one might be a little bit trickier because it's not as obvious, but we do actually have one more hiding here. It's just upside down. So there are actually 7 of these. So you're going to have to sometimes change your perspective. Either that means tilting your head to the left or right, or looking at things upside down. Cannot miss that one, otherwise we get the wrong answer. Now case number 3 is going to look a little something like this. So we're going to have a bigger triangle, let's say like this. So this is how it looks like. Over here. So let's bring that and count how many of these there are. So this is the third case. So how many do you see? I personally see there's one here, there's another here, and there is another here. And this time there are no more that are upside down, because then we would have to go outside the triangle, which is not allowed. So in this case, there are only 3 of these. And then the final case, and we know this is the final case because we can't get any bigger than this one. The final case is actually just this triangle itself. So you can see just this the largest outline here. There's only one of those. This means in total there are, let's add up everything, 16 plus 7 plus 3 plus 1. That is 27 triangles. And we know we didn't miss any because we can't get any bigger than this triangle over here. And we also managed to catch the sneaky ones that were upside down. So I hope by now you're getting used to casework and you see what it is all about. Counting things in a logical, organized fashion. Question number 4 says, how many pairs of positive integers a comma b satisfy this inequality? A squared plus b is less than the number 41. So if we are going to use casework for something like this, I'm going to show you. The way we're going to do this is by fixing a value for a. And why a? Why not b? Well, that's because this a squared is a little bit more tricky to work with than this b. A squared is going to grow larger than b, so I think it's better to focus on that one first. And this is another big concept that carries over into many areas in math. Whenever you see a problem, deal with the biggest restriction first. So when I say I'm going to fix a value for a, it means that I am literally going to pick values for a and set it equal to a. So basically, case 1 will be, let's go with a equals 6. And why am I choosing 6? Well, that's because, by the way, these 3 dots in this shape means because. Well, that's because 7 squared is 49, which is already greater than 41. So if we add a positive integer to 49, which is already bigger than 41, it's just going to keep getting bigger than 41, which is what we don't want. But 6 squared, which is 36, is less than 41. Now, if we set a equal to 6, we're going to get this inequality. Move everything over to one side. This means b has to be less than 5. And because b is a positive integer, that means there are 4 possibilities for the value of b. This means b can either be 1, 2, 3, and 4. And if you've never seen this set notation, don't stress too much about it. I will make another video on that. But basically, it means b is contained in this group. So it can only be one of these 4 values. The important thing is there are 4 possible values for b when a equals 6. Okay? And we're going to repeat this. This time, a equals 5. What happens when a equals 5? What does this mean for b? Well, when we set a equal to 5, 5 squared plus b must be less than 41. And we move everything over to one side. That means b is less than 16. This means there are 15 possible values for b, because once again, b can be anything from 1, 2, 3, 4, ... all the way to 13, 14, 15, but it cannot be 16 because It has to be less than 16, not equal to 16. This tells us that we have 15 possible values for B when A equals 5. And you can see we repeat this process over and over again, because that's all casework is. So I'm going to be going through these a little bit faster. This time when A equals 4. And I encourage you to do this on your own as well with me. This means 16 plus B must be less than 41, so B must be less than 25. So there are 24 possible values for B, anything from 1 to 24, not including 25. Let's see. When A equals 3, this time we must have 9 plus B is less than 41. So B must be less than 32. This means there are 31 possible values for B. I'm going to add another page because I can tell we're going to need more space. And yeah, let's do that. Let's move these around, give ourselves some more space. I hate when everything is cramped together. That's pretty good. Yes, you can keep going. When A equals 2. 4 plus B must be less than 41, so B must be less than 37. So there's 36 possible values for B when A equals 2. Now because this problem has so many cases and we don't want to miss anything, I'm just going to highlight these. So this is not the final answer, but this is something that we have to include in our final answer so that we don't miss anything. Okay? Because we have to go back and, you guessed it, add all of these up. Final case. So you can see a lot more cases this time. 6 cases. So we're not limited to just 2 or 3 cases or 5. Now we have 6. And this one can be finished off easily. This means there are 39 possible values for B. So let me just highlight that too. This means that there are 4, 15, 24, 31, 36, and 39, which is 149 possible pairs AB. A comma B. And we can be sure we got all of them because A is a positive integer. That means this is our last case. We cannot have A equals 0. That is not allowed because 0 is not positive. And as I said before, we cannot be 7 or higher. So everything from A equals 1 through A equals 6. So we got them all. So we can be pretty confident that this final answer is correct. Question number 5. We are almost done. Guys, don't worry. I hope you can see that you're getting used to it though, and it's not too bad. Alright, so this next problem is satisfying our taste buds, it looks like, for casework. In how many ways can Charlie the Chocolate Man give one M&M each to Adam and Mark if he has 3 different red ones, 4 different brown, and 5 different yellow ones, and Adam and Mark, for some reason, they insist upon having M&Ms of different colors. So they cannot both get browns, they cannot both get reds, they cannot both get yellows. So over here, we are going to divide our cases based on possible coloring pairs. So what do I mean by that? Well, what I'm going to do is first we are going to decide the coloring pairs that are actually allowed to be given out. To do that, I'm going to make a very organized chart here. Nothing too crazy, just a little chart. So on this side, we're going to write Adam. On this side, we are going to write Mark. And now what we're going to do is, let's say Adam gets a red M&M. Mark cannot get a red M&M because remember, they must be different colors. So Mark can either get a brown, or if Adam has a red, Mark can also get a yellow M&M. And I'm actually going to space this out just a little bit more because I gave myself quite a bit of room in this chart. Okay. Now let's say Adam got a brown M&M. Mark cannot get a brown M&M. He can either get a red or a yellow this time. And let's say now Adam got a yellow M&M, then Mark can only get a red or a brown M&M. He cannot get a yellow M&M. Okay? Now, these are going to be our cases. So this is case number 1, case number 2, 3, 4, 5, and 6. So let's just emphasize that. We have, sorry, that was terrible. Let me try to make it a little neater. We have 6 cases to cover, so let's count them all. So let's work through this. We got these 6 cases to cover. So first, case number 1. Will look something like red and brown. So conventionally, what this means is Adam comes first, and then Mark. This is Mark's M&M. So RB is going to be this row over here. So let's count. So the question says there are 3 different reds that Adam can get, and then there are 4 different brown M&Ms that Mark can get. This means there are 12 possible combinations. Let's cover case number 2, which is RY. So red for Adam, yellow for Mark. Again, there are 3 different red M&Ms, and I believe the question said there were 5 different yellow ones. Yes. This means there are 15 possible combinations. Case number 3 is the brown-red combination. So there are 4 different brown M&Ms and 3 different red ones. This means there are 12 possible combinations. And do you notice that this case and this case are the same? Well, they're not the same exactly, but I would say they're equivalent because we're just taking the same 2 numbers and multiplying them in different orders. But that doesn't matter because in the end you get the same final answer. So we see it doesn't matter if Adam gets a red and Mark gets a brown, or if Adam gets a brown and Mark gets a red. In the end, these 2 cases are actually equivalent. So this could be a little time saver for us. Don't like how that looks. So this double arrow basically just means equivalent cases. This means if we count one of these, we've basically counted the other as well. So we just need to multiply it by 2. This should help us because now we see that this case over here, red and yellow, is actually equivalent to yellow and red. So that certainly is going to save us a lot of time because now we know that in the yellow and red case, there are also 15 possible combinations. So we really only have 3 different, I guess you can say, types of cases. So that would be the brown and yellow case, which is equivalent to the yellow and brown case. So because I have so much space, I'm going to move this around just a bit. So there are 4 different brown ones and 5 different yellow M&Ms, which means there are 20 possible combinations. Actually, I need some room to write the final answer, so I'm just going to move this up again. And as before, since these are equivalent to these other cases, so I'm actually going to, because I can't have 2 case 3s, let's say this is case 4, and we're just going to write out the other cases. So case 5 is yellow-red. So if Adam gets a yellow and Mark gets a red, it's the same logic. It should be 15, and I'll leave it to you to multiply it out. So write out the multiplication fully. And case 6 is the mirrored version of case 3, so it would have the same answer as well. So there are also 20 ways. So in the end, to answer our question, how many ways can Charlie give out the M&Ms? This means Charlie can give out the chocolates, that's not how you spell chocolates, in, let's add them up, 12 plus 15 plus 20 plus 12 plus 15 plus 20 again, so you can say there's 2 copies of those, so this just helps us save time, and we get a final answer of 94 ways. Excellent. So make sure you see this important part, how these 2 cases are basically equivalent to each other, because that's how you can save time for these casework problems. Okay, I like that one, and let's go to the final problem of the day. So the final problem is about seating arrangements. So this is another popular casework type problem that you might encounter. So we have a few conditions. Looks like some people do not want to sit next to each other. So the question says Amy refuses to sit next to either Beardo or Leonard. Who can blame her? So for those who don't know, these are their names. This is Amy, this is Leonard, this is Beardo. Sky refuses to sit next to Dave. Again, who can blame her? Nobody wants to sit next to Dave. So this is Sky and this is Dave. The question says, how many ways are there for the 5 of them to sit in a row of 5 chairs under these conditions? So basically we have 5 chairs like this, and well, based on these picky conditions, how many ways can they sit? So what I've done over here is I've actually given a valid seating arrangement. So we can have Dave at the end here, Amy next to him because he's not Beardo or Leonard. Sky over here can come next as long as she's not next to Dave, and then Leonard and then Beardo at the other end. So this is a totally valid combination, but this is just one example. We need to find the total number. So for this, what we're going to do is our cases will be based on the different types of chairs. So let me write that out. If you don't understand what I mean, you'll see very soon. So here our cases will be split based on the different types of chairs. So if you don't know what I mean, I'll show you. Let's say we have 5 chairs, which I'm going to represent with this. So these lines, very handy in counting problems, can represent pretty much anything. In this case, they represent chairs. So this chair, we're going to call this the middle chair. These ones over here, they are the same type of chair because they're basically at the end. So these 2 chairs are the end chairs. So they're the same. And then for these 2 chairs, let's just call them the inner chairs, I guess. Because they're not in the middle, they are not at the end, they're just sort of on the inside. Okay. So we're going to fix Amy into these chairs. So let's say case number 1, Amy is in the middle chair. So now we have something that looks like this. So if we have something like this, Amy has to be here. Now let's count how many ways there are for this case. So, because Amy refuses to sit next to Leonard or Beardo, this means these inner chairs, so these two, have to be occupied by Dave and Sky in some order. So it doesn't really matter. You can either have Dave here and Sky here, or Sky here and Dave here. And then at the ends, it has to either be Leonard here and Beardo here, or Beardo here and Leonard here. So basically the inner chairs have 2 factorial ways to be arranged, and the chairs at the end have 2 factorial possible orderings. So in the end, that's a total of 4 ways to arrange the seats if Amy is in the middle. Keep in mind, this is only when Amy is in the middle. Amy does not have to be in the middle. Let's see what happens when Amy is at the end. So she is at the far end of the row. So I'm just going to take this. Did not copy that. There we go. So this time, let's say, I'm just going to erase this. We're going to be going over the case of Amy being at this end, but keep in mind that she has 2 possible choices for the end seat she could be in. She could either be in this end or this end. So she has 2 choices for the end she could be. Now next to her, again, cannot be Beardo or Leonard. So it can either be Dave or Sky. So there's 2 choices of the person who sits next to her. Whether it's Dave or Sky doesn't really matter. The thing is, Dave and Sky cannot be sitting next to each other, which means in this 3rd seat, it must be either Beardo or Leonard. So there's 2 choices for that. And then the last 2 seats can be in any order. So basically the last 2 people can fill up these 2 seats in either the first person here and the second person here, or the first person here and the second person here. So that means there are 16 ways for this case, and it looks like I underestimated just how much space we need. So I'm going to need to add another page. And then the final case, and then we'll have counted all possible seating arrangements. This time Amy is in what we call the inner chair. Amy in inner chair. So I believe I still pasted this. Excellent. This means now this time Amy is somewhere over here. But again, it could be here as well. So basically, she has 2 choices for the inner chair. And because she refuses, again, to sit next to either Beardo or Leonard, these 2 chairs must be Dave and Sky in some order. So whether it's whether it's Dave here, Sky here, or Sky here, Dave here. That's 2 ways. And then the last 2 seats, so these 2 seats, have to be occupied by Beardo or Leonard in some order. So whether it's Beardo Leonard or Leonard Beardo, doesn't really matter. There are 2 ways for that. So in the end, there are 8 possible ways for this case. And because we have gotten all cases, so we've covered every single type of chair, whether it's the middle, the end, or the inner. I feel pretty confident that we got them all. This means that there are a total of, let's see, 4 plus 16 plus 8 is 28. Valid seating arrangements based on these conditions. Awesome. And I'm taking a look over here, and I thought that was the last problem, but it looks like I was wrong because we actually have one more very important thing to cover. This idea of a subcase. So again, a handy little diagram to help you. Subcases are basically cases within a case. So it's like caseception. So basically, you can see we have something like this. So you have a case 1, but that case can actually be broken down further into what we call little subcases. And the process for these subcases is pretty much the same, the exact same as casework. So what you're going to do is you're going to get a bunch of numbers for your subcases. You're going to add them up the usual way, but then that total will not be the final answer usually. It will just be the answer for this first case. So then you're going to have to probably do it multiple times. Case 2 might have some subcases, case 3 might have some subcases, and then in the end you're going to have to add everything up again to get the final answer. If that sounds a little confusing, we must see it in action with a problem. So going back to Math World, this time the alphabet has expanded. So it says they've expanded their letter to 23 letters, A through W, but they still limit their words to 3 letters or less. Okay, so still, no 4-letter words are allowed. Now this time, for some reason, they insist all words contain the letter M at least once. So this time we are asked how many 3-letter words are possible. So not the total number of words, but just 3-letter words. So we don't have to worry about 1-letter words or 2-letter words. So we're still going to approach this with casework. And we're going to split our cases depending on how many M's are in the word. So first, case number 1, we can have words which contain exactly 1 M, but as we'll see, this is where the idea of a subcase comes in handy, because now our subcases are going to depend on the position of the M's. Because if we just take a look with a few examples, so 3-letter words which contain exactly 1 M in the first case, there are many different types that satisfy this. For example, we can have something like this. Let's just make up a random word in this world. Maybe we can have something like this. Or we could have something like this. Or we can have a word that looks like this. And this gives us a pretty good idea on how to split our subcases, because the M can either be in the first position, the second position, or the third position, like I've done here. And I'm actually just going to give it a little bit more space, like this. So this is how we're going to do it. So let's write on the inside, we have a little subcase, number 1. So this one will be words that look like this. So we're just going to put a little placeholder. So first, let's get organized, just underline all of this. So this is actually a subcase within a larger case. So notice that if we have exactly one M, that means these two positions cannot be M's, which means that instead of 23 choices, now we have only 22 for each of them. Basically any letter besides an M. This gives 484 possible words of this form. So let's just specify that, where this little placeholder cannot be an M. Looks good to me. And then we have another subcase, but it's pretty much the same thing. This time the M is in the middle, but we still have 22 choices for the first and third letter. So this is still 484 words of this form. And you guessed it, the last subcase looks something like this. So this time the M is at the end, but we still have it's the same computation, so I'm just going to paste that there. Cool. This means that for this first case, we have a running total of 484, 484, and 484. So that's 3 copies of 484. So this case in total has 1452 possibilities. So let's just highlight that. We're going to need that later, but this is not the final answer because we still have another case to cover. So a larger case, number 2, this time will be words which contain exactly 2 M's. And notice, I want you to realize that there is no overlap between this case and the first case we covered. That's very important. Okay, so this one is pretty much the same logic. I'm actually going to add another page in advance. So now we have another subcase. Subcase number 1 is going to look something like this. Let's say now we start with an M, and then we have something at the end. And remember that this can still not be an M. So this is not an M. This means that we have 22 possible choices for that last letter. Let's take advantage of the space. So, subcase 2 could look something like this. Now let's say the middle slot is empty. There are still 22 choices for that middle letter, anything besides an M. And finally, let's say this first slot is empty. Again, need more space. But there are still 22 choices for that. So that means for this bigger case, we have 3 copies of 22 as our running total, which means that's 66 possibilities for this case. So again, keeping everything nice and organized, we have a 1452, we have a 66, and guess what? We have one final case to cover, but this one should be pretty easy to count because this is going to be the words which contain exactly 3 M's in all positions. So basically, there's only one word that satisfies this condition, and that is simply M, M, M. So this is the only one that we need to consider. And since we're asked how many 3-letter words are possible, this means we just need to add up our 3 mini totals. So we have a 1452 plus 66 plus 1. That gives a total of 1,519 3-letter words in this new alphabet of Math World. And that concludes casework. So, you have some homework over here. And yes, the questions are pretty lengthy, but the only thing I can say to that is get used to it, because you're going to be getting a lot of practice with longer questions. So you have to prepare yourself to mentally withstand it. Now, if you learned anything from this video, it's how to use casework to solve a problem. So you're going to have to do that again for these 3 questions. And if there's anything I want you to take away from this video, it's how to approach these problems in a very organized and logical manner. So if we go through this entire document, we have subcases, we have cases, but basically we just have to stay organized, count things logically, keep a running total, and then add everything up at the end. So I hope I showed many different types of problems so that you can see how to break your cases up. So that should help with the homework. So let's go back to the homework. Sorry, I'm scrolling a lot. Okay. So after you do all this reading, I would say my hint to you for number 1 is to break up your cases based on the number of rooms with 2 people. For question number 2, I would say to break up your cases based on the number of ways that the blocks can differ from each other in exactly 2 ways. So take a good look at this example here, which satisfies the conditions. So we have, in this case, wood and square differs from plastic and circle. So in this case, it would be the material. It would be the material and the shape that differs. So I would break up my cases based on, okay, if let's say the material and the shape is different, or if the material and the size is different, or if the size and the color is different, so on and so forth. Just count them all, break them all up, and then add them up in the end, and then you should get the final answer. And then over here, it's very similar to the triangle problem we did, where we counted how many triangles there were in the grid. You just have to break it up based on dimensions. So maybe those rectangles that look like that, and maybe there's this one too. Don't forget about this bigger one, and maybe something like this, so on and so forth. That's how you break up your cases, count them up, and in the end you should get the final answer. So I think all three problems are relatively doable. Maybe the trickiest one is number 2, because there are quite a few cases for that one. But other than that, I would say if you understood what we did today in class, then this homework should be no match for you. So that concludes this video on casework. Have fun with the problems, and I will see you in the next video. Bye.